So the fact that the correlation does look something like this indicates that there's a certain time shift over which you can say that things are correlated. So we can define what is known as an integral time scale. So the meaning of the integral time scale is that if you integrate Rij, or rather R11, so integral time scale is typically defined for autocorrelation. So R11 is what is used. So if you integrate this R11 over all times, so integral R11 of tau d tau, as tau goes from 0 to infinity, and this is equal to some characteristic time, it is called as a capital lambda, times 1 basically, because everything is normalized. Okay, so this is how the integral time scale is defined. So essentially what this means is this value is 1 and this distance is capital lambda t. So this lambda t times 1 is the area under this blue rectangle, and that should be equal to the area under the white curve. Okay, so this is how the integral time scale is defined. You could also write this as lambda t is equal to, so R11 of tau is basically integral 0 to infinity R11 of tau, capital R, divided by R11 of 0. And this is by definition, this is the normalization that we use. Okay, this is the normalization that one uses for autocorrelation, that is R11 of tau is equal to R11 of tau divided by R11 of 0. And R11 of 0, uh, it will be some proper positive number, it will be some square. Okay, so this is essentially the ensemble of U1 0 U1 at tau divided by square root of U1 0 square U1 0 square, and this is all by definition. Yet another time scale can be defined based on the curvature of this white curve, and that particular time scale is called as the Taylor microscale. And the Taylor microscale is defined in terms of the curvature. So the curvature of this curve d2 r11 by d tau square. So this is sort of proportional to 1 by some lambda t square. Okay, this is what I mean. This is what you get because R11 is dimensionless as per this definition. So this should be proportional to this, and the Taylor microscale is defined precisely as lambda t square is equal to minus 2 upon d2 r11 by d tau 2 at tau equal to 0. So it is the radius of curvature, you if you may, at this particular time. So it helps you in telling whether a curve is something like this, something like this. Okay, it helps you in ascertaining that fact, something like this. Okay, so that is that. But I mean, these are all ad hoc definitions. This is nothing very physical. These are all ad hoc definitions. But regardless of being ad hoc or not, they help you in providing insight into the temporal or spatial structure of how well things are related. Let us move on to the definition of a spectrum. So the energy spectrum is defined in terms of Fourier transform. So Se is the energy spectrum, and this is equal to 1 by 2 pi integral minus infinity to infinity times the Fourier transform of R11. So this tells you what is the sort of energy content with the frequency omega in a given correlation, autocorrelation R11. So this kind of interpretations, it will be clearer to you when you undertake your course on transform calculus. But for now, just remember that this is by definition, and this is just the Fourier transform, and we are calling it energy spectrum, and it will be clear why. So now, any Fourier transform is defined in terms of the inverse pair as well. So R11 tau will be defined as integral minus infinity to infinity Se omega exponential of I omega tau d omega. So this is what the pair is. I mean, you may find in many books 1 by square root like this in both terms, but there are, it's just a matter of convention. Okay, it's just a matter of convention. I choose to not write this particular term and write everything over here. So according to this definition, if we choose tau equal to 0, so set tau equal to 0, so this becomes R11 of 0, and this is minus infinity to infinity Se omega, and this becomes 1, this entire term becomes 1 d omega. So R110 is by definition u square. Okay, this is by definition u square. So this becomes u square is equal to integral minus infinity to infinity Se omega d omega. And this means that the total integral of the wave, not the wave, but the spectrum over all the frequencies. So this is integral of the Fourier transform over all frequencies, and that is giving us the fluctuation squared. Okay, u. So this is giving us the fluctuation squared, and the fluctuation squared is nothing but the energy content of that fluctuating component, and that is why it is called as an energy spectrum. So similarly, Se0 is obtained by setting omega equal to 0. It is 1 over 2 pi integral minus infinity to infinity R11 of tau d tau, and this is equal to um, so I've basically set omega equal to 0. So what do we have? Basically this goes so 1 over 2 pi, so this becomes twice of 0 to infinity R11 of tau d tau, and this you can write because statistically R11 of tau and R11 of minus tau, uh, let uh, let us prove that as well. So R11 of tau is basically integral u of tau or u of 0 times u of tau d tau, not d tau. This is not integral, this is simply going to be the ensemble mean. R11 of this is also equal to u of minus tau u of 0. I've just shifted the other waveform. I've kept this waveform at 0 and shifted the duplicate waveform to minus tau. So, and this is by definition also u of 0, u of minus tau. And hence R11 tau is equal to R11 of minus tau. And that is why we can make this of from 0 to infinity and to this 2 component over here. So this becomes 1 upon pi integral 0 to infinity R11 tau d tau. And this entire thing by its very definition, we can write it in terms of the integral time scale. So SE of 0 is 1 over tau integral R11 tau d tau 0 to infinity, but recall that the integral time scale is equal to integral R11 tau d tau upon R11 0 to infinity, and this gives us this integral, so 1 upon pi. So this integral is R11 at 0 times lambda t. So R11 at 0 is basically u1 square ensemble average times the integral time scale divided by the constant factor pi. So the energy contained in the zero frequency thing is this, and it is related to the fluctuating kinetic energy. So this is basically the fluctuating kinetic energy. This is basically the integral time scale. Okay, this is what. So everything is related, and the reason behind things being related is that basically you are decomposing the time series in the terms of a Fourier in terms of all the Fourier components, and all of them are related to one another because things are correlated. If they're uncorrelated, none of this would have happened. So how do you actually get this time signal? So if you have a domain, you want to find out. So if you want to find out the cross correlation between the velocity at this point and the velocity at this point, you need to put a probe over here, right? You need to put a probe over here as well. So once you have two probes, you can take two time signals. One is this, the other is going to be this, and then you do the correlation and all that. But if you just have one probe, you say you put the probe over here, and what you can do is you can move the probe quickly. You can move the probe quickly to this point. In moving the probe, you are basically, what you are doing is basically you are sampling. You are getting, surely you are getting a time series. Something you will be getting, but this time series must be interpreted in the sense that at this particular time you are moving. So if you are moving with a velocity u naught, okay, so if the velocity u naught is sufficiently larger than the velocity of the flow, then this time series can be converted into a space series. So by assuming that because this overall flow is smaller than the probe movement speed, in the time the probe takes to move from this point to this point, the characteristics of the flow have not changed. So this assumption is called as the frozen field assumption. So this time, if you want to convert to space, so this will be equal to x upon u. So with the help of this, you can get the time signals at different x points at a given time instant. Okay. So this is how you do it.